Okay, let's now look at where to use UDP and where to use TCP. Right, UDP is used by request and reply applications where the data is minimal and retransmission can be done quickly. If it is important that all the data arrives and that it can be processed in its proper sequence, TCP is used as the transport protocol. So most, let's just say all the applications that we use, they either use TCP or they use UDP. We also have cases where both protocols are used as a hybrid. So you use TCP as well as UDP for that same application. But where do you use UDP only? Where, which type of applications? So required protocol properties right here, we have fast, low overhead, does not require acknowledgements, does not resend lost data, deliver data as it arrives, unordered. Then for TCP, reliable acknowledges data. I think we went through that. Right transport layer protocol for the right application. When to use UDP? Number one, let's just go through that. Let's go with UDP first, and we'll look at probably a number of applications. Number one, we have real-time applications. Real-time applications, for example, streaming. If you are streaming, you need a protocol which uses less overhead because streaming is real-time. We want to border England. Uh, it's also have a little bit of delay because obviously of all the transmission from the UK, there's that slight delay. But how will it be if probably on a buffering inoitwa iri kuloadha kunge YouTube iri kungomira yozocontinue, but you're watching a live match? What will happen is team inogona to go yoita 2-0 in without you knowing because of the type of protocol that is being used by your application. If you're using TCP for live streaming, that will probably happen. Zvekuti kana pasina connection, inotombopoza, it loads, it buffers, all of that happens. Then yozocontinue, you are behind. That is not ideal for streaming. That is not also ideal for example if you're using voice over the internet, VoIP. If you're making a WhatsApp call, another example. The protocol that we're using is UDP. Why? Because we have real-time communication. If we have real-time communication, we will need a protocol that is fast, that has less overhead, a protocol that does not resend lost data. Imagine a case yekuti utaura nemunhu WhatsApp call, munhu ataura kuti hello ndepi, iwo unozvinzwa, then acknowledgements are sent back kuti munhu adzokorere futi kuti hello ndepi. With the live communication, that is not that is an issue. So the protocol that you are supposed to be using there is UDP. Tikasatongonzwa hatina kutongonzwa. It is what it is. Probably the person on the other end, and you have to repeat. But if we have a protocol that does that for us, then our communication will be very, very difficult. So we have real-time applications which prioritize speed and can tolerate data loss, but in very small cases, small data losses. Right. So What property allows UDP to do this? One, it's fast, it has less overheads, it does not resend data, it delivers data as it arrives. Also does not send acknowledgements. So for applications with real time, we have UDP being very useful. Other applications, we have what we call request and reply. Request and reply applications. For example, you have protocols like DNS. So we already mentioned VoIP. With this protocol here, DNS. You see that in DNS, the data exchange is very minimal. There is not a lot of data that is being exchanged. Basically, the messages that are being exchanged is, I have this IP domain, I have this domain name, x.com. I want its IP address. So you send this, that's the request. Then you get a reply with the IP address. That is minimal data exchange there. There is not a lot of data that is being sent. The protocol to use at the transport layer is UDP. That's one, minimal data exchange. Two, retransmission can be quickly done. So if I've sent this and I don't get a response, it's very easy. I can send another one until I get a response. So for these type of applications, these type of protocols as well, UDP is the preferred protocol to use at the transport layer because it simplifies communication that way. We have a lot of protocols actually. It's not only DNS which uses UDP. A lot of them uses UDP. Right, let's go to why TCP. So for UDP, real-time applications, one. Two, request and reply applications. Request, reply. Then you definitely need an application which is fast. No retransmissions, quick retransmissions if there is no acknowledgements that are being received. Let's now look at TCP. When do we use TCP? We use TCP because it's reliable, it acknowledges data, it resends lost data, it delivers data in order. So we have applications that require reliability, applications that require data is sent in order. Number one, applications like web browsers, they use TCP. Why? Because data is in order. Some of the errors when you search for a website, when you search for something, some of the errors that you get is because data is not in order. With UDP, you can send information, and if there is some data missing, message you know with UDP, no problem. However, with TCP, you can send the information and there is a segment which is missing from that information. Then you won't be able to view that information. You won't be able to view, you won't be able to hear, you won't be able to see that information. That's an error. There is need for retransmitting that low segment until you get a full packet. So with TCP, it's mostly for applications that require that reliability. Example of those applications, web browsers. Web browsers, they use TCP. And that explains the reason why, even if there is no connection, if you are loading a web page, let's say network provider down. If network get up, let's say slow, let's say down. Network provider slow. What happens? Page no loader, no number is loader, no number is loader. If the network improves, page no loader kusvika razobuda rese. The reason why it does that is because of this protocol known as TCP. There is some acknowledgements which are being sent pauri kuloadha paya kuti information yakati isati yasvika ngaisvike, then yasvika yozotanga kuitwa in order. That's how you get to see the pages that you are requesting. Dai raishandisa UDP, what will happen is pakati transmission information yagona kusvika wongoona half page, rimwe rese roregera kuuya, and that's it. No retransmission haridzoki. So with applications that where there is need for reliability, like web browsers, we have to use TCP. You also realize with emails, they use TCP. That's why we have protocols like these ones here. SMTP, they use TCP. HTTP and HTTPS, they also use TCP. Right. We also have applications that use pre-recorded videos. For example, YouTube. This one uses TCP. Unlike live streaming, if you are live streaming is UDP, but if you are on YouTube, you are using TCP, which allows you to pause, to reload, to buffer at times. I think TCP basically offers more user experience. It's more flexible with user experience. You can play around with the applications. UDP does not have that. You cannot pause a live stream. If you pause a live stream, then paunozesa on is probably iri kutangira but the current session, current video inofanira kunge iripo palive stream. UDP and TCP. Right. There are also applications that use a hybrid approach. So they use both TCP and UDP. The reason why, obviously, probably you have an application that requires that little bit of reliability, and it also needs to be very fast. So what do? You use both. For example, video conferencing, for example. Video conferencing. It's not actually streaming, live streaming. It's not that. It's not a pre-recorded video as well. So you can have both protocols working there. Why? UDP, so that you have less overhead, it's fast. There's an element of live there with video conferencing. There is an element of being live, but we also use TCP to offer reliability. Kuti kana video pasina connection inokwanisa kumbobuffer, and you get to continue listening pamberi bichana. That's video conferencing. We don't necessarily need it to be live with video conferencing. It's also not a pre-recorded session. It is live, but we're using both UDP and TCP. I hope you get what I'm saying. With video conferencing, there is both of those protocols being used so that you have probably an experience which is much better than having a live stream. Because with a live stream, network you get down, that's a problem. With a video conference, network you get down, inokwanisa buffer, and you get to listen to all the information that is being sent, that is being communicated. Right. Let's have overview of TCP. Typical questions that you will get are questions like you are given an application and we're given how that application works. And you are asked which protocol will be suitable for this type of application. Well, what you need to look at is, with this type of application, do I require reliability, or I need it to be fast transmission wise? With this type of application, do I need acknowledgements, to send acknowledgements so that we can have retransmission, or there is no need for that? Those are the things now you'll be looking at. The properties, overhead. Do I have a problem with more overhead? Do I have a problem with bandwidth? If you have a problem with bandwidth, then probably TCP is not an ideal protocol for you, because UDP, less overhead, much efficient use of the bandwidth. So you analyze, you look at those properties, that leads you to what type of protocol to use for specific applications. TCP features. TCP establishes a session, ensures a reliable delivery, provides same order delivery, supports flow control. I think we've basically gone through this. With establishing a session, we have the three-way handshake. We'll look at it later on. TCP is connection oriented. It negotiates and establishes a connection between source and destination prior to forwarding any traffic. Before any messages are sent, the actual message, the actual data you want to send, there is an exchange before, which establishes a connection. Reliability, we've gone through that. Acknowledgements, sequencing. For many reasons, it is possible for a segment to become corrupted or lost as it is being transmitted. TCP ensures that the segment that is sent by the source arrives to the destination. How does it ensure this? Acknowledgements, resending of those lost segments. Because networks may provide multiple routes that can have different transmission rates, data can arrive in the wrong order. Using sequence numbers, data is reordered so that it has the correct order. Network hosts have limited resources, memory, and processing power. When TCP is aware that these resources are overtaxed, it can request that the sending application reduce the rate of data flow. I think this one, we get to look at this one in detail. Flow control. Basically, if at layer 2, the way we approach flow control is, if you have two interfaces, two ports, one is using, it has a speed of 10 gigabytes per second port speed. The other one, it has 100 megabytes. If the 10 gigabytes forwards traffic to the 100 gigabytes at 10 gigabyte per second speed, it will be impossible for the 100 megabytes to take in all that traffic. There is need for flow control. So how does flow control work? At layer 2, basically there's communication between the two devices. I have port speed 10 gigabytes. Me, I have port speed 100 megabytes. So let's agree on a speed that both of us can use. We are going to be using 100 megabytes because 10 gigabytes is capable of reducing its speed. That's how flow control happens at layer 2. We'll get to look at how flow control works in layer number 4. It's a bit more complex than the one at layer 2. The header. So the TCP header is mainly made up of all these things that are on the diagram. TCP is a stateful protocol, which means it keeps track of the state of the communication session. It records which information it has sent and which information it has acknowledged. Right, header redu rine a couple of fields. We have the source port, destination, sequence number, acknowledgement number, header length, control bits, reserved field, the window, the checksum, the agent option. Then we have the application layer data. Okay, going down there. This is a typical header for you. Like what we did with layer 2, you were supposed to know what every field does. With layer 2, we had your preambles, your SFDs, your destination and source MAC address, you had your information, then you had your fields for error check, FCS. I think I'm leaving one or two fields there, but you're supposed to know each and every one of those fields and what they do, what are they responsible for. All right. This is a brief description of all the fields that are in the TCP header and what they do. The source and destination port, that's very easy. We have a 16-bit field which is used to identify the source and the destination port numbers that are used by the application. We'll look at the port numbers. It's not the same as, these are logical ports. It's not the same as those ports that you see on the switch. These ports, your first Ethernet 01s, it's not those type of ports. These are logical ports with port numbers ranging from 0 to, it should be 65,000. I'm not sure. I know it's 40 something thousand port numbers. I think we'll get to look at that later on as well. A lot of port numbers that we have. So applications, they have specific port numbers they use. For example, we have my well-known port numbers, HTTP. It uses port number 80. So every time there is communication and you see port number 80, then you know HTTP is being used. We have FTP, which uses 20 and 21. FTP, we have DNS and DHCP. What does DNS and DHCP use? DHCP. I think DNS, there is one which uses 53, yeah. I'm hoping it's DNS. DHCP, I'm not so sure. There is 23, it should be Telnet, 22, SSH. You need to know popular protocols, popular applications, and what are the port numbers that they use. That will be very important going forward. Uh, DNS 53. What is DHCP? DHCP, I'm not so sure. All right, let's continue. We have the sequence number. TCP header fields used for reassembly purposes. We've gone through that a lot. Acknowledgement number used to acknowledge information. That's the field for that. Header length, the length of the header basically. The length of the header, we have the reserved, which is just a field reserved for future use. Control bits, we have some flags, which indicates the purpose and function of the TCP segment. So here with control bits, we have the most common flags. We have sync, we have acknowledgement, ACK. So if a flag is saying sync, it's a TCP segment which is used to establish connection, synchronize. You get a response with ACK, which is another flag for acknowledging received information. So this control bits field is mainly for those flags. Window size used to indicate the number of bytes that can be accepted at one time. The window size will be very critical when we explain flow control. Very critical when we explain flow control. The checksum used for error check, the agent field. If our data contains agent data. Then that is indicated in the agent field. We also have a flag agent if we have information uh that is agent. If we have data that is agent in our segments, right? TCP header fields. Applications that use TCP, we already mentioned this one: web browsers, emails. FTP, file transfer, SSH needs to be reliable. It uses TCP. You also realize applications that needs security, applications or protocols that are secure. You realize most of them, they use TCP because it allows for that. TCP handles all tasks associated with dividing data streams into segments, providing reliability, controlling data flow, and reordering segments. It's important to know for every application what is its preferred transport layer protocol. Very important. Typical exam questions, you are given a number of applications, identify which ones use TCP, which ones use UDP. Now looking at UDP, UDP has the following features: data is reconstructed in the order that it is received. Any segments that are lost are not resent. No session establishment. The sending is not informed about resource availability. This is what leads to congestion. So with TCP, we said there is a connection. It's connection oriented. Starting point. A session is established. Before any information is sent, a session is established. There is an exchange that is done there. We call it the three-way handshake. Some of the information that is in that three-way handshake is, as a device, this is how much traffic I can handle using the window size. That field, which we call the window size, it is used basically to say, this is the amount of traffic that I can handle. So if I'm communicating between A and B, I send my synchronized segment, then this one responds. That response will include information of, this is how much information I can take. So when A is sending information, it will take note of the window size, which is basically the amount of information that B can take. Therefore, that is what avoids packets being lost because of congestion. Basically, that is what flow control is. It starts with an exchange of messages during session establishment. With UDP, however, the sending device is not informed. Saka kana iri kutopusha traffic yakawanda, that traffic will be lost. Because UDP as a protocol, it does not care if you lose packets or you don't. Its header, you can see, is a bit smaller. With the 1 year, with the 1 year TCP, mukatasa panapa, typical questions well. Your TCP, again at 20 bytes. This one, it only has 8 bytes. It's a bit smaller. Source, destination, port, the length, and the checksum. Acknowledgement, apasina. Sequence numbers, apasina. All the flags, control bits, apasina. What else? Quite a number of fields that are still not there. Let me see. Right. So by UDP, this is no longer there. This is not there. No flow control. This is not there. Checksum is there. Header length. No. 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 That's why it has less overhead. It does not have a lot of additional information that is added to the data. Source port, destination port, length, and checksum. I think we've gone through that already. But this length gap is there. Length is still there. Let me see. Here the length. This is still here. 1, 2, 3, and 4. Right. We now look at applications that uses this UDP, DHCP, DNS, SNMP, TFTP, VoIP, video conferencing. We also learned that video conferencing can be used plus TCP hybrid. Why? So that we have a better experience with our conference, video conferencing. These are some of the applications and protocols that use UDP. Live video multimedia applications. Applications that tolerate data loss but require little or no delay. Examples, VoIP, live streaming. Simple request and reply applications, we went through that. DNS, for example, DHCP. You send a request, a discover message, minimal data. You send a discover. If it is not received, you resend. It's very simple. But if you are sending a lot of information, resending that information will usually be inefficient because you are using a lot of bandwidth. So the reason why we have UDP applications is basically for having little overhead, having applications that are rapidly transmitted, simple request and reply applications, for example. Applications that handle reliability themselves, unidirectional communication where flow control, error detection, acknowledgements, error recovery is not required or can be handled by the application. Examples, we have TCP, TFTP, and SNMP. So we have other applications which are responsible for their own flow control, error detection, and error recovery. Those ones will use UDP because some of the work that is needed is being done by the application itself. Port numbers titled multiple separate communications. So TCP and UDP transport layer protocols uses port numbers to manage uh, multiple conversations. Not sure what is written here. Just a minute. Let me hide video panel. Right, multiple simultaneous. So TCP and UDP transport layer protocols use port numbers to manage multiple simultaneous conversations. The source port number is associated with the originating application on the local host, whereas the destination is associated with the destination application. So if I'm trying to send an HTTP request, I'm trying to communicate with a web page. This is A. Right. We have device A, we have device B. What is the source port and what is the destination port? So if I'm communicating with the HTTP application at device B, I want to communicate with that from device A. My source will be a random port number mostly. That will be my source. Then my destination will be the application that I want to get access to. In this case, HTTP port 80. So port numbers, they are very useful to separate communications. Communication that is destined for port 80 is for HTTP. Communication destined for port 20, that is the control information for FTP. DNS, port 53. That's how communication is separated. Even if it's one device can have multiple applications. I think we've mentioned that. Can have multiple protocols being used at the same time. How does the device know and how does it know how to track all the communications that are happening of all the protocols? How does it know that? That's where we are with the transport layer. That's where we are with the use of port numbers. Every protocol, it has its own port number. Every application, if you want to communicate, every application will have its own port number. So that's how we are able to separate multiple protocols, multiple communications between devices. Socket pairs. The source and destination ports are placed within the segment. The segments are then encapsulated with an IP packet. The combination of the source IP and the source port number, or the destination IP and destination port number, is known as a socket. That combination is very important for communication. Sockets enable multiple processes running on a client to distinguish themselves from each other and multiple connections to a server process to be distinguished from each other. So basically, sockets, here they are. Let me see. So pineapple, we have information here that we see in the pineapple. Uh, Let me decipher this. We have FTP, we have an FTP connection, we have a web connection. This is our source. This is our destination. We are trying to send we are sending information using two applications. We want to demonstrate how our sockets are helpful in separating or in multiplexing, demultiplexing some of this information. Right, in this diagram, or let me start by defining the socket. Basically, socket is a combination in source port number and source IP address. For example, Panap, this is a web connection. The source port is this one, the destination port is this one. A combination of this source and this one. That is what we call a socket. In literatures, you see it written as this 192